Okay. Hello, my name is Josh.
My name is Anderson.
I'm Megan.
I'm Ashley, and our lab name was Contact Force Normal Force and Frictions.
After calibrating our force sensor, we wanted to test the normal force at different angles. First, we calculated the normal force at 90 degrees, and the equation F equals mg cosine of theta helped us with this. We held the board at 5 different angles and pulled the force sensor with 500 grams attached to it perpendicularly to the board to calculate this. Calibrated this to 500 grams, and we're going to record the normal force, picking it up off of a 90-degree angle. And we can do that by just pressing record and then picking it up. And then we record the highest spike. You can see the highest spike will be about 5.3 newtons. And yeah, now we're gonna record different normal forces with 500 grams the same way on 5 different angles.
Using the goniometer, we measured the angle to be 7 degrees. And while you're pulling with the force sensor, make sure you're pulling perpendicular to the rim.
Alright, so now we just raised it, so we have an angle of
11 degrees.
11 degrees. Now we're going to use a force sensor to look at the weight.
Okay, so our next angle is 16 degrees, and then when you pull it up,
Our fourth angle was 21 degrees. And we pull it perpendicularly. We get 44.91 newtons.
So our expected slope was 4.89975, and then we measured the actual slope of 5.3274, and then our percent error was 8.7%.
We wanted to prove that our normal force is proportional to the cosine of theta, and our graph showed this because it is going up in a linear fashion, and our r² value is close to 1.
Alright, so in activity 2, we measured the coefficient of static friction using 2 different methods. And so the first method, we kept the board flat and we used a Pasco force sensor to pull the block horizontally right about until it starts to move. And so by doing that, we calculate and we can find the maximum force being recorded through that. And so we can calculate the static friction for that by using static friction equals Fs max over mg equation. And then we repeated this for 10 more trials and then to get an average value. And we also recorded the standard deviation and standard errors for this trial and method.
We're gonna measure static friction using the force sensor attached to the block, and then measure the coefficient of static friction.
2, 1, go.
Oh, okay.
Just a little.
Alright, so in our second method for activity 2, we placed the block on an inclined plane and slowly raised one side until the block was right at the verge of sliding. And so right when the block starts to slide, we can measure that critical angle using a goniometer, and using the Fs max equation of static friction now equals the tangent of the critical. And so then we can repeat these measurements by adding on mass to the original block, showing that static friction doesn't depend on mass.
So we added weight on the car, and we started with 50 grams, and then we went up to 100, then 200, 300. We did 20 grams as well. Sorry, we started with 20. And yeah, so we did that.
For activity 3, part 1, we used the concept of constant acceleration, and we had our block on top of our wooden beam, and we attached the force sensor to the block and pulled with a constant force. Using Pasco, we measured the force for each trial, and then also measured the coefficient of static friction using this force with the equation F over mg, and then using each coefficient of static friction, we took the standard deviation and standard error.
Three, two, one, go.
Okay.
For activity 3, part 2, we gave impulse to the block that was horizontally on the board, and using a photo gauge sensor with this initial impulse, you then measure the distance between the initial and final distances, and we use the equation A equals v squared over 2d to get the acceleration, and then we were able to find the coefficient of static friction using A over g. And using this, we can use F equals ma because the static friction is the only horizontal force.
And the distance is 16.9.
So in our experiment, some errors that could have occurred are misreading the measurements from the ramp angle. This could have been a lack of precision from our eyes or just not being level with the table and the goniometer. And then the surface of the wooden beam that we were using could have been uneven, which would have affected the friction on the ramp at different areas. In activity 1, we had to pull the force sensor perpendicularly to the angle of the ramp, but we can't guarantee that we pull it at a 90-degree angle every single time. And the calibration of the Pasco system could have also been wrong, which would be a mistake of the machine. In activity 2, an error that could have occurred was when we lifted the ramp at an angle. We had to hold the angle ourselves, so the angle could have varied at different points in time when we were trying to keep it in place. We also, when we tried to pull the block until it barely moved, the judgment of our eyes of when the block moved could have been wrong, and we also pulled probably with like an inconsistent force each time, even though we tried our best to keep it very consistent. In activity 3 in part 1, we tried to pull the force sensor with a constant speed, but we can't guarantee that we did it at a consistent speed every single time, which would be a human error on our part. And then when we pushed the block through the photo gate, we had to push the block with a force, but that force could have been inconsistent each time we pushed it through.
As you can see, Josh just slid down that railing. It's a good thing he was wearing jeans and not leggings or basketball shorts. He would have flown off. According to Blue Scientific, there are micro and macroscopic irregularities on surfaces, which determine contact points between two surfaces. Therefore, increased contact points on rougher surfaces tend to lead to greater resistance. So rougher materials and rougher surfaces tend to have a greater friction than smoother materials.